Daniel Bourque from PMC.
Thank you very much for the information and for the introduction. As you said, Daniel Bourque, I'm with PMC, design build mechanical contractor here in Atlantic, Canada. We have an office in Halifax and one in Moncton. I have loved buildings since I was a kid. My dad was like a GC, and I was always, well, why does it work like that? What does it, how come it does that? And try to take things apart as much as possible. I was talking on the front row here about like, oh, you come to heat pump conferences on your vacation? Absolutely. If I was on vacation, I'd come to a heat pump conference. I do an all-inclusive in Mexico, and then I've got like this gold band on. That means I'm like prestige or whatever. What am I going to do today? Am I going to go on the waterfall or something like that? And they say, Senor Bourque, what can we do to make your day more enjoyable? I said, can I see your chiller plant? And he said, Senor Bourque, I have no idea what you were talking about, but I will make that happen for you. And so, yes, I enjoy this. Oops, here we go. And I've been doing buildings as a design build mechanical contractor or as a consulting engineer for the past 24 years of my professional life. So PMC, as a mechanical contractor, we do installations and we do controls, very heavy in the controls for various air-to-water systems. And when I was asked by Martin saying, hey, we kind of had something fall, thank you, something fall between the cracks, are you available to give a presentation? It was absolutely. He said there's very strong interest in air-to-water, and I said, well, we've done a whole bunch of them. I can give a case study. The question is, the audience is uncertain. So are people coming to this conference because they want to know about heat pumps, or everyone's an expert in heat pumps and they want to know the latest? So there's a few slides at the beginning just to kind of set some ground rules and some understanding if you've never seen a heat pump before. Okay, so a quick background and overview, some design considerations, stuff that we've seen when we're selecting heat pumps for some of our projects, or that when we've collaborated with some consultants to select the heat pumps, when we talk to the vendors and the suppliers about what their heat pumps are. So these are all the questions that we ask. And then we've got a few case studies of projects that we have installed, and we'll just show you how air-to-water heat pumps are being used in HRM Halifax region, and we've got one project in Moncton. So, talk fast. Okay, so very basics. A heat pump, we are moving energy between two sides. We have an evaporator, we have a condenser. It's always the misnomer of, the evaporator is what's happening to the gas inside. The gas is evaporating. The condenser, it's the gas that's condensing. And then a heat pump, I guess depending on your definition, doesn't technically need a reversing valve, but often has a reversing valve to allow you to change what's happening in your evaporator and your compressor. So the heat pump system types, there's the air source and the water source. The water source, heat source, is rejection only to water. So you, that's what we're talking about. We're a water source heat pump, usually water to water. Air source, there's two kinds. You have water to air. Water to air is what we typically see in homes, what we see in most commercial. We're trying to make air a certain temperature. Air to water, and the focus of this presentation, is we're trying to make water a certain temperature. That is the focus, okay? Now, how are we doing this with the heat pump? We saw in an earlier slide, we have the compressor, we have the evaporator, the condenser, and the heat valve. 5 years ago, the breadth of options of manufacturers was not there. Currently, there's more and more air-to-water systems that are there, and a lot of the manufacturers who are doing VRF are saying, well, how can we get in on this? How do we optimize and make water? Yes, mini splits are nice, but if we want to sink into a water loop, a hydronic building, and so there are the hydro units, such as this, where you have an outdoor unit, and then you have refrigerant piping that comes inside the building, and you have a hydro box or a hot water generator. There's different types of those. Some have an extra compressor, some do not. There's some manufacturers, Mitsubishi in particular, I don't know of any others, that have kind of a bit of a hybrid, where they have, instead of the refrigerant piping going throughout the building, you're going to go from your outdoor condenser. I'm leery about touching this now. The outdoor condenser, you only have a few refrigerant lines that come to a special box that is hybrid, and you have water loops after that. So it is air to water through refrigerant. It's not a packaged unit, but that's fine. And then you have the packaged units, or the monoblock units, where everything essentially sits on the roof. It's in one big box, and the water, or the glycol, in our case, in our climate, goes directly outside. It's usually, but not always, they'll have the V coils just to save space, or just like like some of the residential ones, it'll wrap around and you have the fans on the outside. For these monoblock units, there's common configuration. You have two pipe, and that you can see, this is the same manufacturer, a set of shop drawings. Here you see only two connections, and it happens to be a modular unit. So you have 1, 2, 3, 4 modules, but each module only has one in and one out, okay? These units are heating or cooling. I'm making cold water, and then when you need it, I'm gonna make hot water. If you have like a regular heat pump loop, where you have your water to air heat pumps, or your water source heat pumps, for like a commercial building or for a residential system, this could be both your cooling tower and your boiler, depending on what season it is, whether you need to heat your loop or you cool your loop. So it's like an air source chiller, and it can be like an air source boiler. It can be either. It is lower cost than the next one, which, spoiler alert, it's going to be the 4-pipe systems, because you have less heat exchangers, less machinery on the inside. But for a 4-pipe system, you can heat and or cool. It depends on what the predominant load is. You can do heat reclaim. You can be cooling some space, and with the rejected heat, you can just push it out the other side and heat some heating loads with that. It is more versatile, but it is also more expensive. And that's the difference here. You see, on each of these 4 modules, I have an in and an out for cold, and I would have an in and an out for a hot water loop. Okay? So if you have these 4-pipe systems, you'll see you have like a heat exchanger inside. These little arrows represent water coming in and out. I'm coming at 12 Celsius, I leave at 7. Hey, I've got this compressor over here. I'm trying to cool. I'm compressor over here. I'm trying to cool, and it figures it all out internally. If I'm in predominantly heating mode, the whole system is running in heating mode. My little 4-way valve, my reversing valve has now switched, and now I am rejecting heat to the heat exchanger, and I'm sucking the heat from outside. And for those very few hours of the year that we all strive for, if you have a perfectly balanced system, you have the same heating load as cooling load, you can never need to reject heat or suck heat from outside at all. Everything is happening just within the 2 heat exchangers. And then, of course, I've got a little bit more cooling than heating. Hey, you can do that. A little bit more heating than cooling. Hey, you can do that too. depending what we've seen on drawings, what we've seen from talking to manufacturers, and as a contractor trying to get the costs for some of these systems, if you're looking at a 4-pipe system, it's important to know, well, the magic is when your loads are balanced. Hey, my cooling load is the same as my heating load. If you can know what your winter cooling load is going to be, you have some big electrical rooms, you have a server room, you have a garbage room that you refrigerate and you keep lower. If you know what you are going to be cooling year-round, that might make sense to have a 4-pipe system for that. Depending on the manufacturer, it's like, hey, we've talked to them, you should get a 4-pipe system that matches your winter cooling load. And then just get a 2-pipe system for the rest of it. It can be either cooling or heating, and it's going to be a lot cheaper to do that. Yes, you have an additional electrical connection. Yes, you have another crane, you have the curb work, but typically it ends up being slightly less expensive depending on the capacity. If you've just got like 30 tons, well, it's going to be a lot more equipment. Okay, so some design considerations that we've seen, and being the controls contractor, the people who try to make it all work, when on paper it's nice, but in reality, not always as nice. It's, in the first year of my career, I went to a recommissioning course at NRCan, and the saying that stuck to me is, in theory, there's no difference between theory and practice, but in practice, there is. You have to think about it a little bit, and you're like, oh, yeah, it's true. So for most manufacturers, you're going to have a design temperature envelope. Oh, I can make such and such temperature water down to, minus whatever outside. I can make hot water down to such and such temperature. But these are kind of an envelope. The unit can work up to there. You don't always want to be working at the envelope. So beware the edges of the envelope. My car, it's a Corolla. I think the red line is like, 6,500 or 7,500. That's the limit. I'm going to shift into like 5th gear so that I can get the RPMs down. I'm not trying to keep it at that limit because I want the Corolla to last a little longer. The same thing for flow requirements. Most manufacturers have a min-max flow requirements. Beware the edges. Hey, we bought this big chiller and it can go between, or air-to-water heat pump, I can go between 700 and 1,600 GPM. And it was selected at 750. So, okay, we'll do 750 GPM. You go at, the chiller's tripping off. It's tripping. The heat pump's tripping. Why? Because it's at the cusp of, I don't have quite enough water for these outdoor conditions. Oh, it got a little bit hot out. Well, it's going to back off a little bit. So if you're riding at the edges, system can do it, but you're more likely to have problems. And please, 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 only one edge at a time. I can go up to 170 degrees Fahrenheit, and here's my flow rate range. Well, don't go to the edge of the flow rate at the same time you're going to the edge of the temperature rate when you're making your design selections. So from some manufacturers, you'll see something like this. This is your leaving water temperature, in heating. And so I can leave at 30 Celsius, 35, 45, 55, up to 60 at an outdoor temperature of minus 20 up to 45 outside. If you can stay in the middle most of the time, knowing that you're gonna fluctuate with outdoor temperature, don't try to design a system, hey, you know what? I need 55 degrees all the time for my system. And so, hey, look, the system can do it at minus 20, 55, perfect. This is the piece of equipment for me. Well, it may be a piece of equipment for you up until, minus 15, minus 16, minus 17. Ooh, it got to minus 21 outside. Well, you're hooped. So beware beware the edges. Okay? Or have a contingency plan in place, a backup system. You need a little bit less capacity or a little bit less a temperature if you can. Same thing for chilled water. They're going to say, hey, at an outdoor temperature, you can do that. This manufacturer says, ooh, if you want to have your leaving water temperature below 5 degrees, well, you got to have a glycol. You want to have it below 3 degrees, you got to have some kind of a brine there. So it's kind of easy for you to see as a designer, as an installer. If someone gives you a heat pump, hey, install it, you got to make sure that it's got the brine in it or the glycol in it, otherwise you're going to have issues. And then, of course, simultaneous. Beware the edges, but also beware the corners, where it's really, here's my leaving water temperature on the hot side, and here's my leaving water temperature on the cold side. If I want to make the hottest water possible and the coldest water possible at the same time out of the same, hey, you can do it, but as a contractor and the controls contractor trying to get these systems to work without the trips, without the resets, without the second stage unloading, without the pressure reliefs coming off, try not to do super hot and super cold at the same time. And then when you're looking at them, yes, I can operate at those temperatures, but are you getting the full capacity out of it? So the temperature may be one thing, but you're not getting the BTUs. So this is another manufacturer. They say, hey, look, I've got the full heating capacity even at 36 F2 Celsius, and then after that, it starts dropping off to roughly half. Okay? It's still going to do great at minus 13, but it's only giving me 64,000 as opposed to 136,000. So temperature can affect the performance. Other temperature considerations. Certain heat pumps are designed for a given delta T, a delta temperature. The rule of thumb is, chilled water, 10 degrees, a boiler, 20 degrees, all that kind of stuff. As engineers, as manufacturers, everyone's like, can we stretch it a little bit? Can we make it 30 degrees? Can I help my return temperature come, we want to get away from that low delta T syndrome. So can I make my temperature as big as possible? Well, there are some manufacturers, this one's Mitsubishi, they have two heat pumps, they kind of look the same, and they're just like one letter off, the QAHV and the CAHV. And the Q and the C, it's even the same sound. So you're like, well, what's the difference? Well, this one happens to be CO2 as the refrigerant, and they want as high a delta temperature as possible. This is designed for domestic hot water systems, where I'm coming in cold, cold, cold from the city, and in one shot, I get my entire delta T. I don't have the storage tank where I slowly build up, slowly build up. I mean, I will. I'm going to come into this tank, and then this guy is just going to recirculate with this one, which is designed just for a 20-degree delta T. And this one is going to slowly heat up this tank. But I'm doing everything in one shot with this heat pump. So that's one manufacturer. There's manufacturers of custom equipment that we've purchased that are designed specifically for 30. Hey, I can do, you're afraid of the envelope, Dan? We can do as cold as you want. We can do as high temperature as you want, but I need my delta T. If I don't have the delta T, weird things are going to start happening. And so the control system, we say, oh, how do we figure that out? So there are temperature differentials to consider of what the machine wants to see. And there's also flow considerations. So in the event that you have a modular system, this is similar to that one that we saw at the beginning when I had the 2-pipe and the 4-pipe. I've got 1, 2, 3, 4, 5, 6, 7, 8 together. Well, in this scenario, I've got a pump here, with a VFD because I'm saving energy and stuff like that. That's awesome. Now you're coming into this heat pump. As soon as you want the second heat pump to go on, what happens to this pump? Is this pump, do you have a solenoid here isolating the other ones? Are you going through all of them at the same time? And so this one has, this one's on, you get 20-degree delta T, but it's going through these guys at the same time. It's just passing through. And so I have my 20 degree divided by 8. Oh, now I only have a 1 degree or a 2 or 3 degree delta T. What about, hey, I open this valve. Well, as soon as you open I open this valve for heat pump number 2. Awesome. Do I ramp this guy up right away? Is this pump controlled on a delta temperature between inlet and outlet? Is it based on a pressure? There's a lot of issues when we're staging various pieces of equipment that have solenoids to make sure, as soon as you open it, that first one that was operating, it's going to drop down, and you're going to have, you start playing within that envelope. That's why if you're designing at the envelope, as soon as I kick on number 2, well, that flow rate is bouncing around a little bit. So watch out for that. And then there's other ones where they bolt them together, and you have a common header at the back of them. So this is a 2-pipe. They have the different manufacturers also have them in 4-pipe, but you have the same flow rate going through here. Now, if you want to vary your flow or something like that, well, it has to know before it starts kicking on extra stages. So these are some of the issues that we've seen as a contractor installing these systems, trying to get them to work for temperature and flow. But if you are sizing the heat pumps, I mean, we do the load calcs for the building. We say the building needs a load of 200,000, 500,000 BTUs or kilowatts or whatever your system is. If you go and look at the presentation with Mike Riddler later on, he's going to also talk a lot about the thermal storage, because if you have the thermal mass, like in the passive houses, right, just on the other side of the partition there, you have a thermal mass, you store the heat really well. I only need a tiny little heat pump to kind of edge me over. If I have a huge ton of thermal mass, maybe I only need 1 module or 2 module. If I have 0 thermal mass, I may need a whole whack of these. And so whether you're looking for a system that's going to do building heat, or you're looking at a system that's doing domestic hot water, the thermal storage that you have, those mass tanks that you should have in your systems, are going to be important. But the manufacturers have these tools. So there's reports. This manufacturer says, well, look, we looked at this date, and for system type 1 or building type 1, this is like a condo, this is a school, this is whatever. Well, here's the amount of hot water that I use per day, and this is the amount, based on the year. So from a calendar year, from January 1st to 31st. That's kind of the scatter of where it is. And well, we're pretty comfortable sizing a hot water heating for this. There's a little bit over, but I've only got 7 days out of the year where I was a bit above. That's good enough tolerance for me. Other manufacturers, they'll have something like this, where they'll say, okay, here's a 2-day profile. Let me look at my storage remaining and a recirculating tank temperature. They'll say, well, listen, I've got my heat pump, and then I overshoot a little bit, but then, I start running into it. And as I start having more and more load, my tank temperature, the storage capacity drops. But then my heat pump just hums around and just keeps going fairly constant. And over time, here I go. I've averaged it out with this, the average of this orange line, for example. They show here, run status. It's on, continuous, on. There's no supplemental heat running. So just the heat pump running all the time, when it's at its most efficient, I haven't purchased too much heat pump. And so manufacturers, use them, give the manufacturers good data. Don't just say, I need 100 tons. Seriously. Well, I've done it before, it's fine. Do the calculations, do the math. If you're getting 100 tons, know what your margin is on that. Can I maybe run at a lower temperature, do different things with my flow? So there's sizing tools. A free one that is government sponsored by, in the States, I think some Canadian research contributed to it. We've used it as like a first crack and stuff like that, put the QR code in case people have their phones, so oh, we're gonna wanna do that. And it's not shooting by, so you got a chance to do it. So it'll say, what water temperature do you have? What's the design cold temperature? Do you want to supply? Do you have any storage? What type of system do you have? Do you have, a quick tank and then a recirc tank? Do you have what do they call it? I can't see that small. They have like a parallel, they have these saddle tanks, they have different ways of configuring your system, which are common to most manufacturers. And then they'll say, okay, based on that, this is how much heat pump you need, and this is how much storage you'll need. Typically, it's for domestic water use, but you can also do it for like building heating loads and stuff. Okay, so let's get into about halfway done. Some of the case studies of projects that we have worked on. 323 Sacville Drive, a domestic hot water application. There's 2 outdoor units, Glycol outside, water inside, 2 backup boilers, and 4 storage tanks. So kind of had to piece it together there to zoom in so that you guys can see. Up on the roof here, I've got 2 heat pump units. They're piped in air to water, and again, the water is going straight outside. So this is like a monoblock system. Coming here, I've got a pump that's going to deliver water up to these guys, and then here's my heat exchanger. So on this side, I've got my glycol tank here. This is all glycol, and on the other side, right up here, we have domestic cold water coming in. It goes right into these tanks to get preheated. This is kind of like a first stage, second stage, and I've got 2 electric boilers here as kind of backup to make sure that, should something happen, I'm not sure, we're not always privy to some of the calculations. Sometimes designers, and an electric boiler is a lot cheaper than a heat pump. So you'll say, hey, I want that heat pump to run, like we saw a couple slides back here. I want my heat pump to run almost continuously, and if I get a little bit of a peak, I'll just hit that with an electric boiler or something like that. Depending on the nominal size, right? This is my system. I have 30 tons of heat pumps. Well, the next module, it goes up in steps of 15. Am I going to get a whole extra module just for that little bit of heat that you need during peak hours? Let's deal with an electric boiler or get a bit more storage. So we're seeing more and more of these types of systems where we're having for domestic hot water heating and or preheating. So this one was done by Darcy, Darcy O'Connell, I think, at Sacville Drive. And there's some other surprises in the room here. So this one, Carlton West Eventide. This is a different manufacturer of heat pump. This is just to show that, yes, we took it from engineers and they designed the whole system. It's not just throwing it together. Again, domestic hot water application. This one has 3 outdoor units. Again, glycol outside, water inside, but the backup is a little bit smaller. For space, you can have multiple tanks, and I know that's a big consideration. Well, how big is the tank? Can I get the tank out of there? Can I get the tank back in there if the bottom rusts out in 10 years, 15 years? Can I just put it on a dolly, or do I have to start disassembling walls and getting cranes and stuff to take out these mass tanks? Is it up in the top penthouse, or is it down in the basement? So this one, fewer backup boilers, 1 large storage tank. So this one is a split system. So the only thing that's outside is just the condenser, and then you have the refrigeration liquid, refrigeration suction going to an interior hydro box, something that is going to, I didn't talk about that earlier, but some of the hydro boxes are just making hot water. You can usually get up to about 140 Fahrenheit or so. Some of the hydro boxes have an additional compressor. And so they will boost the temperature. I've got one compressor out here. I got a second one here that'll boost it up to 170 plus degrees. So I'm not sure which this one was, but have the outdoor unit, each one going to its indoor unit. The indoor unit has its own little circulating pump. And so that's easy to say, well, how do I turn on an extra stage? Well, this guy's going to click on his pump, and then he's going to get the flow that he needs. So you have a few more pumps in your system, but at least each unit is kind of getting what they want. Then this is direct water inside, and then go to a heat exchanger, and then here's all my hot water storage, that one large tank. There's the electric boiler, your pressure, your three-way temperature valve, and then the controller. So, the previous system, we've got the liquid, the glycol going right outside, a monoblock unit. This guy, we have the split units. Another case study up at King's Wharf, courtesy of MLE Engineering. It's marked up quite a bit because we physically installed this one. So this one, it's an air source boiler application. There's two outdoor units which are split type. They're custom units that were designed specifically for the Delta T and for the application. There's one boiler, but it has multiple stages, multi-pumps inside, that kind of stuff, and one very large hydronic separator. And instead of all these buffer tanks, this is not domestic hot water. This is actually building heating loop. It's like, you've got a cooling tower, or in this case, a dry cooler and a boiler, and you have all these heat pumps in the building that you're trying to maintain your loop somewhere between the famous 60-90. So this is the schematic. There's a few more things. This is going out to the building on this side here, so that's going to all the hundreds of heat pumps that are there, and you've got a little boiler, and clearly not to scale, but this is the gigantic air-to-water, the gigantic hydronic separator. So it's the same liquid that's going down to the units that's going to come up to the heat pumps. Here I've got there's my boiler here, and then I'm coming out here. This is an air-to-water condenser. So there's a brazed plate heat exchanger, and there's refrigerant that goes outside to the compressors and the evaporators and the fans and stuff like that. Just a couple lines coming in, and then it's separated, so I don't need glycol for this heating system. Not in that part. However, I do have two fluid coolers or dry coolers, and those are going to be sitting outside all winter, and that system needs some glycol. So that's just to cool down the loop. I've got the heat exchanger here, so you've got some glycol in this system, and so that's cooling it. So all the heat pumps, if they want, their range between 60 and 90 or whatever, if I need to reject heat, well, I've got the fluid cooler. If I need to add heat, I'm going to start with my air source boiler, or my air source heat pump, and then supplementally, you have a natural gas one. This heat pump could have been selected, designed at additional cost and complexity to also be a heat rejector. So instead of using your fluid coolers, maybe I only needed one fluid cooler, and then this guy could have a heat pump. Then you get into your whole engineering analysis. Is it worth it? I'm using the compressors for a little bit longer. Why would I want compressors to reject the heat outside if I can just have a fan, right? So it's a question of economics at a certain point. So that's what it looked like schematically. And then we went and we laid it out with this giant hydronic separator here. Coming in from the building, you've got a bunch of pumps that's just pushing out to the building. Then your first connection here to your boiler, your next connection that's going to go out to your fluid coolers. And then over here you have your air-to-water brazed plate heat exchangers, number 1 and 2, for the units that are just sitting outside. And I've got a couple of photos of that. So when I say large heat exchanger, they actually had to cut a hole in the, or redesign the structure in of the roof to be able to maybe eventually get it in and out, because it really takes up the whole height of the mechanical room. There's not really any other way to even tilt it down. I think like all the air vents and stuff, you try to tilt it down, it's gonna scrape off. So contractors want to optimize for cost. They want to make it as, their buildings as compact as possible, but based on how they come from the shop, that's what we had here. And so these guys here, that's the condenser, that's the heat exchanger that is going to the air-to-water system outside. So all the hydronics are done, all the controls are wired in and stuff like that. Here's from another angle. You can see, here's my heat exchangers outside. That's the air-to-water system. I've got one more photo, and that's the condensers. And there you go. They're still wrapped. They're not yet commissioned. This is from last week. So we have all these copper lines, these refrigerant lines that are going to go and connect to those set of heat exchangers. So that was, an existing, a new building that is designed with an air source boiler. Another case study, this is in Moncton, 814 Main Street. You've got, again, an existing system. You've got a heat pump loop, you've got a cooling tower, and you've got a pair of boilers. Very, very classical, but one of the boilers died. So do we just replace it with another boiler? Well, listen, I've got all the connections, all the taps. Why don't I try to put in an air source boiler? And so that's what we had based on the configuration. Again, we were looking at hydro units. So we had the higher temperature indoor units here that are connected for the sake of, the site and whatever. They're connected onto that leg of the boiler so that we can come and get what we can out of these guys. And then if there's any additional heating required, the boiler's going to handle it. So they're in series with the boiler. And then physically, that's how it kind of looked in the sketch. They wanted an option, if we're doing all this efficiency stuff and we're adding heat pumps, well, maybe eventually we're going to want to add solar. So we had to look at the clearances between where the heat pump condenser could be outside and the various arrays, and look at, make sure that the outdoor unit's getting enough airflow and that it's breathing properly. And that's the picture out here of where we thought it would be best suited. So this project it is going ahead. We haven't, I think we've gotten the heat pumps delivered on site this week or something like that. So we'll see how that goes. And with the support of a Efficiency Nova Scotia pilot project, we also have a case study of my house. So I had an oil boiler, and there was a pilot project to say, people are coming into homes and contractors saying, well, your best bet for, a heat pump, let's just add a mini split here, and then one over here, and then, one over here and one here, and you'll need like 5 heads, 7 heads. It's just like, golly, that's a lot of, I've got an existing system. I've got cast iron radiators, or I have fin and tube on the perimeter. Why can't I just add a heat pump to this? Well, until recently, the air to water wasn't, there weren't that many manufacturers doing it. And so hence the pilot project, and also to say, well, what's it going to cost? And, the formula for mini splits is very well known. It's cut and dry. Efficiency has a good idea of how much money they're actually going to save, so they can figure out how they're going to compensate that financially. Okay, you're going to have a payback, but, we're going to save some energy, and we're going to chip in a little bit. But for air to water, it wasn't certain. The house that we have is 1958. Yes, it has asbestos plaster on the walls, so people are like, well, just go to these low temperature air to water systems, it's going to be great, and just replace all your radiators. I had so many offers to replace all the radiators. I'm like, dude, I have to abate my whole house. I got to move out of my house. I got to go to a motel or a hotel for a month. Like, this is not going to work. And so when we found an air-to-water that did high temperature a couple years ago, I talked to the people at Efficiency. I just talked at the right time. Pilot project was closing. And it always seemed, yes, there's some grant money, but you've got an old house. All you have is the radiators. I don't have an ERV. I don't have any ventilation system. I don't have any ductwork. It'd be a shame to spend, 40, 45, 50 grand on a heat pump and still kind of swelter a bit in the summer. Can't we get some cooling at the same time? So the solution that, after probably too much research, landed on was outdoor condenser, and it's a VRF system through Samsung that comes to a high temperature hydro box here, making 176 degree water even at the coldest temperatures outside. And then I have two ductless splits that are going to do the upstairs bedroom, the big master bedroom right opposite the door so that it can go towards the kids' rooms, and the main living room. And the system was, there was hydronic. It wasn't as easy as you pull out the boiler and you put it in, because the system was done a little weird. The ground floor, it's 20 degrees, it's beautiful, thermostat is satisfied. The basement right next to the boiler, 24, 25, because all the piping is uninsulated. You go upstairs, in the peak of winter, it was like 12 degrees upstairs. And we had a monoflow T system, and it was a creatively installed monoflow T system, and so the water flow wasn't getting to upstairs. I'm like, well, if I'm going to the trouble of adding the heat pumps and stuff, let me just kind of cut at the ceiling of the basement and then go and have a bit of a manifold, and then I can get to each radiator individually. Happen to work for Contractor, so yes, this is helpful. I have now 8 zones instead of 1 for the whole house. Yeah, so that's what we have. And then our plumber really likes drawings. He's a very visual person, and so to say, well, is it going to fit? Is it going to fit? It wasn't just do the schematic and have it lay it out. We spent $3 of painter's tape, a Dollarama, and we came and we put one unit here. That's the hydro unit. Here's the storage tank and the indirect heater for domestic. And the loop, as the red line, my heating loop, goes from the bottom of the tank, coldest water, is coming into the hydro unit. Then it's going to come up here into a 12 kilowatt electric boiler, and then come back down into the top of the tank. I have my domestic coming in here into the bottom of the tank, and then it loops around. I have a coil down here, a coil up there, and it goes to the 3-way mixing valve. Oh, because with the oil boiler before, you just have the heat exchanger plugged into the side. We had no mixing valve, and so when we had guests over, I was like, hey guys, don't let the hot water run and then test it, because you will burn your fingers off. And so just like a 3-way mixing valve, hey, wouldn't you know, it makes for less burns. And then the green loop is now the hydronic distribution. So I don't have an updated photo of that, but we've got a pump there, and we've got a pump for this system, all the various control valves, balancing valves for each one. And again, being a controls contractor, we have quite a few temperatures at the top, medium, and bottom of the tank. We have a temperature coming in and out of this, in and out of the boiler. We have flow meters, so once it's up and running this winter, we'll know where the energy's going and who's keeping their room a little bit too hot. So that's for heat pumps. There's the last slide saying that we also, for air-to-water heat pumps, PMC also has a lot of experience with VRF. These are some of the statistics that we pulled out when we did a presentation at Greenbuild Atlantic in March. So we're pretty familiar with heat pumps. So that's the end. Thank you. Any questions?
What kind of hot water temperatures did you get out of that air to water heat pump system at your home, and how did that end up working for you? Or I don't know if you went through a full winter or not. Did you say that you would like integrate cooling into that system for you somehow as well?
Yes, it's one of the reasons I wanted to have a separate controller is because the heat pump, you have a thermostat for the unit, and it says, well, what temperature do you want the loop? And you can design an indoor-outdoor curve, and it's going to follow that. But if I have a backup boiler, the backup boiler has an indoor-outdoor curve, which doesn't exactly align. You can tweak the ends of your curves a little bit, and so we ended up designing. It's only been installed recently. We have not yet done a winter with it. But when we were testing it out, I was getting, in the summer, 150, 160 degrees Fahrenheit without issues. But all we're doing is domestic water. And then we kind of toned it down because it's essentially an on-demand system. I took it down to 120, and people weren't burning themselves. They were pretty happy. And yeah, so the cooling integration is on the refrigerant side. So it's like it's a VRF system. So it's like having, a multi-head unit or something like that, where you've got the outdoor condenser that's doing, the upstairs head, the downstairs head, and then the basement heating head. But they're all in the VRF. It's all kind of sequential Ys and Ts and stuff as you go along. So yeah, there's two heads. And, the goal was heating. So we got heating, and then all manufacturers have their own ratios of like, oh, you can have 130% or 50%. And so, we got as much cooling heads as would fit into the ratio. They're 9,000 BTUs. They're kind of small. You don't really feel cool coming off of them, but if you set it to dehumidify, that's all we wanted in the summer. So, any other questions?
Is your hope there to not run the electric boiler? Is this backup?
Absolutely. Absolutely, and it's sized for that. We did the heat load of the home. We did the regression for temperature for the oil bills and the heating degree days and stuff like that. And we counted the linear feet of baseboards that we had to know what temperatures, and we need about 46,000 BTUs.
Did you say you had cast iron, or was it?
Cast iron, yeah. They're cast iron. They're like the low, like 1 foot Wheel McLean ones. They're not the big curly ornamental ones. So this is 48,000 BTUs. I need 46, and these are whatever I could get on the same condenser.
Have you done any calculations on if that was just regular fin? Like you said that you looked at fin, but
Yeah, but is as best as abatement. It's like, yeah, you could.
okay, right.
Actually, the ground floor and the upstairs is all cast, and then they added one fin in the basement and fin in the room above the unheated garage with the thermostat in the basement next to the boiler. So one kid is like smoking hot, and the other person, their room was like 8 degrees in like the peak of winter. And like, we got to do something about this. Like the thermostat's in the wrong spot, but how do you integrate it all? Oh, just run some wiring. Gotta. Any other questions?
So how do you expect the energy bill compared to your previous oil boiler?
The energy bills, I think slightly less than half. If I had done, taken that heat exchanger out of the side of the oil boiler and just had a straight resistance electric hot water tank, I think at the oil prices and the electric prices, it was roughly even. And roughly even, but then I can turn my my boiler off all summer long, so I don't have the standby losses of oozing through there. So, kilowatt hour for a kilowatt hour, B2, I think roughly 40%. That's what I'm hoping.
2 questions actually. First one, what point are you kicking the boiler on? Like what is your determination of 5,000 to be on?
So the hydro unit actually does heat fairly quickly, so it kind of comes up to temperature. And with the control system, I've just set an offset there. So I've set an offset of like, I think 4 degrees F. So say I want to maintain 120, and if it ever gets down to 116 or 115, the electric boiler will kick on, kind of as a stage. Because the issue is, it's not a heat reclaim system. I mean, it's just a home, but you still have to schedule, either you schedule, hey, I'm going to make my hot water in the morning and in the evening when there's showers and dishes being made, or you're cooling. So, you know, it's the middle of the day. People want a little bit of dehumidification. The system is in cooling mode. And when is it going to get out of cooling mode? Well, when the last head that's had a demand kicks out of cooling mode. Well, it's the summer, so that's not going to happen. So at night, you turn off those systems, or now we've gotten an adapter to schedule it, and then we can schedule heating or cooling. If it was commercial, sure, you'd have that branch box or that mixing box. It's going to allow simultaneous heating and cooling, but come on, it's a home. I mean, it's a lot. That's what I had planned originally, and then when the cost came in, I'm like, how often in the summer am I going to be cooling and wanting to make, like, it just, that was not a financial decision that made sense. So we just said we'll schedule it at different times. There's another question over here somewhere.
So you talked about this being for your cast iron radiator system. Does a system like this work for the baseboard fin systems, or what would you have to change to make that work?
Yeah, it would work. I mean, you wouldn't necessarily need the high temperature one. You may be able to get by, I don't know whether the cast iron needs a higher temperature, the fins need a higher temperature. Yeah, so if you could make do with like the model for Samsung, this is an HT, you could do the HE, which allows a lower temperature. But if you're allowed the lower temperature, there's lots, especially nowadays, downstairs when I just saw at the trade show, there's lots of units that are making 140 degrees, no problem. So you could have a monoblock system. You'd have to then weigh, do you want to fill your whole system with glycol? Do you want to have a heat exchanger somewhere in between? If you do add the heat exchanger in between, now this system loop is very tiny. Does the manufacturer have an issue because, oh, I need thermal mass in this loop? Some manufacturers do. They're like, well, I understand that you're connected to the other system, but it's the other side of the heat exchanger. I need my system to have so many GPM per ton, and I need my system to have 5-10 minutes of water or glycol in the system. So you could go to a monoblock system, absolutely. But, and then, you know, monoblock system, now all these, you have liquid in them. That's fine. There's like, I saw the Daikin Altherma, they have, it's water, and then instead of being just split heads here, they're fan coils, essentially. So you have chilled water in them. And so then, again, when am I heating to preheat my domestic system? When am I cooling to go to these systems when it's in the summer mode? In the winter, everybody's in heating, so it's fine. So yeah, if you can do with a lower temperature, there's way more systems, especially now, since the research. Any other questions? And that is exactly noon. I believe the next thing on the agenda is lunch and networking downstairs. So thank you very much for coming to the symposium and for listening. And I'll be around if you have any further questions.